बिस्मिल्लाहिर्रहमानिर्रहीम। वेलकम बैक टू मैथमेटिकल मेथड्स ऑफ फिजिक्स। आज हम इसका लेक्चर नंबर 24 पढ़ेंगे। बिफोर स्टार्टिंग दिस लेक्चर, लेट्स सी व्हाट वी हैव स्टडीड इन द लास्ट लेक्चर। We continued with the Fourier transform. This is what we studied in lecture before the last lecture. Fourier sine, cosine and inverse Fourier transform. In the last lecture we studied properties of Fourier transform, and I proved 2-3 properties and left couple of properties for you guys. Then we studied convolution theorem for inverse of the product, and then we used Fourier transform method to solve partial differential equation, especially the diffusion equation, and we saw a couple of examples of diffusion equation. Today we will continue with the solution of partial differential equations with the help of Fourier transform method, and we will in particular see the solution of wave equation and the solution of Laplace equation. That will be our scheme of study for today's lecture. So let's start with the solution of partial differential equation using Fourier transform, and the first one is the solution of wave equation. We have solved wave equation for with separation of variables method and with Laplace transformation method. So this is the third technique we will be using to solve partial differential equation, and in particular the wave equation. Let's consider an example of the wave equation. Example is compute the displacement uxt of an infinite string using the method of Fourier transformation. Infinite string means you are not fixing your string from 0 to L or from minus L to L. You are letting it go from minus infinity to infinity. It's an infinite string. Given that the string is initially at rest, so what does that mean? Initially at rest means the velocity at t is equal to 0 is 0. So partial u by partial t at t is equal to 0 will be equal to 0. And that the initial displacement is f of x. It means u itself is equal to f of x when t is equal to 0. No boundary conditions are given. The reason is boundary is at plus and minus infinity. And we already have conditions at plus minus infinity that u and partial u by partial x, they both vanish at plus and minus infinity. Because far away there won't be any disturbances. So there won't be any displacement. Alright? So it's a very reasonable condition imposed at plus minus infinity. So all I need are two conditions, initial conditions at t is equal to 0, which is ux0 is f of x and utx0 is 0. These are two conditions given. So if I formulate this problem, the displacement of this infinite string is governed by the partial differential equation, which is the wave equation. Utt is equal to c square uxx. Now x goes from minus infinity to infinity. Subject to the initial conditions, ux0 is equal to f of x and utx0 is equal to g of x. No boundary conditions are given, because boundary is at infinity, and we will impose the conditions that u and ux go to 0 as x go to plus minus infinity. So taking the Fourier transform of the partial differential equation, we have clearly what is the Fourier transform. I wrote it in the integral form. You can just write f of utt c square f of uxx. So we know that the Fourier transform of uxx is iota alpha square, right? Iota alpha square u alpha t. So that gives you negative c square alpha square, and utt is the second derivative of u, capital U, because with respect to time it's just the derivative. We don't put any formula. So all I got is this. This was negative c square alpha square, that's why it became plus c square alpha square on the left. And because alpha is a parameter here, so we can write this partial derivative as the ordinary derivative for u with respect to t. Now this is a second order. In heat equation, in diffusion equation, in last lecture we got the first order ODE, but now we are getting the second order ODE just because of the second time derivative involved in the wave equation. Alright, so what will be the general solution then? General solution will be, what are the roots here? M square is equal to minus c square alpha square, so m is plus minus iota c alpha t, right? Plus minus iota c alpha t. Or you can write so your general solution will have either cosine and sine form, cosine c alpha t and sine c alpha t, or you can write e to the power iota c alpha t or e to the power iota c alpha t with minus and plus sign. Now the constants c1 and c2 will generally depend on alpha. They will not be just constants, because you see the roots have this parameter alpha, so your constants can have the parameter alpha as well. So in general I can write phi tilde, phi hat alpha and c hat alpha. Alright, here we took phi hat and c hat are arbitrary functions of alpha instead of constants. Now to get the answer uxt, I need the inverse transform, right? We need the inverse transform. If I take the inverse transform of the above equation, what I will get? 1 over square root of 2 pi, this whole function multiplied with e to the iota alpha x d alpha. Alright. So here with c alpha it becomes iota alpha x plus ct, and here e to the minus iota alpha x minus ct. So you got x plus ct and x minus ct. So what is this? This is the Fourier transform of phi hat x minus ct. The reason is I can replace this x minus ct by some variable y. Then this will become alpha will become x minus no, it is actually, you see, this alpha and this alpha is common. So this is a new parameter x minus ct. So if you integrate this whole thing, you will be left with x minus ct. X minus ct. Alpha will be gone. So this whole thing will be a function of x minus ct. This whole thing will be a function of x plus ct. Alright. Now if we use the initial conditions, what was that? That ux0 is equal to 0? No, it was f of x. It was ux0 is equal to f of x. So it means at t is equal to 0, you get phi of x plus c of x is equal to f of x. And the second condition was utx0 is equal to 0. So this gives you the derivative minus phi prime of x plus c prime of x is equal to g of x. Alright? So from here, what you are getting is, from here, if you integrate the second equation, because we are getting the derivatives on the left hand side. To get rid of the derivatives, I need to integrate. So if I perform integration on the left hand side, it will give me minus c phi of x plus c of x is equal to integral of gx dx. But because we are integrating it from x naught to x, so I can replace this dummy variable to anything else. Let's say tau here. G tau, d tau. Tau goes from x naught to x plus k. And I divide this c on the right hand side. Now you see I got phi plus c, and here I got minus phi plus c. If I add these two equations, I'll get c of x. If I subtract these two equations, I'll get phi of x. So once by adding and then by subtracting, I will get phi x given by this and cx given by this. So I got these both functions in terms of f and g. Now if I substitute these values of phi x and cx in the above solutions, in this solution, phi x and cx were unknown. I got the values of phi x and cx. If I replace, I'll get this solution. Right? See, phi of x is this. So I need phi x minus ct. So x will be replaced by x minus ct. This x will be replaced by x minus ct. Similarly, here I need x plus ct. So here x will be replaced by x plus ct. This x will be replaced by x plus ct. So all I got is this. Alright? K by 2 can be cancelled because this is minus k by 2, this is plus k by 2. So at the end I got this thing. Alright? Now this simplifies to 1 by 2 fx minus ct, fx plus ct, and plus 1 over 2c, because you see this is minus. If I compensate this minus and start from x minus ct to x naught, and then from x naught to x plus ct. So it means I can write this as one integration from x minus ct to x plus ct. This is called the Dalembert solution of the wave equation. This is a well-known Dalembert solution of the wave equation. It's written as D'Alembert's, but we pronounce it as Dalembert. Dalembert solution of the wave equation. And this is a traveling wave solution basically. This is a wave traveling to the right, this is a wave traveling to the left. It's a traveling wave solution as well. Alright? And now if our initial condition, if I took the general conditions fx and gx instead of 0, 0, but given at the beginning, you see ux0 is equal to fx and utx0 is equal to gx. I took these conditions. But if your string is initially at rest, this gx has to be equal to 0. If I take gx to be equal to 0, then this term will drop out. This second term will drop out, and all I'm left with the pure traveling wave solution. Only fx minus ct and fx plus ct. Alright, so this will be my solution if gx equal to 0. So one of them has to be non-0 to get the non-trivial solution. If f and g both are equal to 0, then 0 is the solution. Alright, then nothing is happening to the string. It will stay at rest. That's it. So let's solve this equation now. Obtain the solution of the free vibrations of a semi-infinite string. Now it's given semi-infinite string, 0 to infinity. Same wave equation, subject to the initial conditions, the same initial conditions. u0 equal to f of x and ut at t0 is equal to g of x. So what will be the difference? What will be the difference with this equation and this equation? The only difference is the domain of x. X goes from 0 to infinity. Alright, so 0 to infinity, I can use either sine or cosine transformation. So let's solve this equation. So we have utt is equal to c square uxx for 0 to infinity, t positive. Initial conditions are ux0 is equal to fx and utx0 is equal to gx for all x between 0 to infinity. And now at x is equal to 0, it's not infinite boundary, it's a finite boundary. So we can assume that at 0 your string is fixed. It goes till infinity, right? So let's say at t equal to 0, x equal to 0, your string is fixed. Now because u0 is mentioned, string is fixed at x is equal to 0. That is uxt at x is equal to 0 is equal to 0. Now again this thing suggests Fourier sine transform, not the cosine. Fourier sine transform. Because for Fourier cosine transform, I need partial u by partial x at x is equal to 0 equal to 0. Alright, so if I take the Fourier transform, sine transform of 1, so to solve, take Fourier sine transform of 1. Fourier sine transform of 1 is Fourier sine transform of utt alpha is equal to c square Fourier sine transform of uxx alpha. Now utt becomes the second derivative, that's it, partial 2 by partial t square of Fourier transform of u alpha is equal to c square, and the second derivative, if you remember, Fourier sine transform was negative 2 by pi alpha u xt at x is equal to 0, and then minus alpha square Fourier sine transform of u alpha. Alright, this was. Right, we proved it in the last lecture. We proved it. What is the Fourier sine transform of partial 2u by partial x square? Since the string is fixed at x is equal to 0, this will go to 0. So this drops out. So I'm left with minus c square alpha square. And let's say the Fourier sine transform of u is us alpha t. All right. So here it is second derivative of us alpha t. All right, so this is what so this is the ordinary differential equation. Here if I want to write simply, if I simplify it, I can write it c square alpha square us is equal to 0. Second order ODE. All right, so again auxiliary equation is m square plus c square alpha square is equal to 0. So this implies that m is equal to plus minus iota c alpha. So again, either you can write in terms of cosine and sine or e to the power, whatever you want. So therefore, us alpha t is equal to, so ut is equal to, it's a pure imaginary, iota c alpha, no real part. So constant times cosine c alpha t plus another constant times sine c alpha t. And now I am calling it constant, but basically they are the functions of alpha. Alpha is a parameter here, so in general they should be the they should depend, these constants should depend on alpha and beta. So so they are basically the functions of alpha, not exactly the constants. Now initial conditions are ux0 is equal to fx. So if I take the Fourier sine transform, will give you us at alpha 0 is equal to capital F alpha. Similarly, second condition was utx0 is equal to gx. So again Fourier sine transform will give you, because Fourier transform does not affect the time derivative, so it will become just the time derivative of I can write partial by partial t, because ust it will be little confusing, the time derivative of us, so I can write partial by partial t instead of us. All right, or d by dt is equal at alpha 0 is equal to capital G alpha. These are the, f is the Fourier transform of small f, g is the Fourier sine transform of, in particular maybe you can write fs and gs. S indicates the sine transform. So these are the two initial conditions now. So now from star u at alpha 0, us at alpha 0 is equal to cos 0 1 and sine 0 0. So it is a of alpha. This will be equal to fs alpha. So I got one value, and dus by dt at alpha 0 is, what is the derivative? Cosine is sine, so sine 0 is 0, and this becomes cosine. So cosine c alpha at t is equal to 0 becomes 1. So I'll get b alpha times c alpha. So this is c alpha b alpha is equal to g of alpha. All right, so from here I got b alpha is equal to 1 over c alpha gs alpha. So therefore star becomes, us alpha t is equal to a alpha, which comes out to be fs alpha cosine c alpha t, and plus b alpha is 1 over c alpha gs alpha and sine c alpha t. So this is your solution, where fs and gs alpha are the Fourier sine transform of small fx and small gx respectively. So now you need to take the inverse Fourier transform, right? To get uxt back, need to take inverse Fourier sine transform. So inverse Fourier sine transform will give me uxt back, but what will be the Fourier inverse transform? 2 by pi, right? 2 by pi 0 to infinity capital US alpha t and sine alpha x d alpha, right? Inverse Fourier sine transform will give me uxt. So now I can replace the values of US alpha t. US alpha t is fs alpha cosine c alpha t plus gs alpha over c alpha sine c alpha t times sine alpha x dx. This is what you got. Now cosine alpha and sine alpha being multiplied, sine alpha multiplied. So I can convert this product to sum. Cos c alpha t times sine alpha x will become cosine 2 times sine into cosine is sine alpha plus beta, plus sine alpha minus beta as well. So I can, if I replace this product by sum, I can obtain, or I can write this solution as the first term is sine alpha x cosine c alpha t. I am writing them separately and then I will convert to product. Otherwise it will be confusing. Gs alpha by cs c alpha sine alpha x and sine c alpha t dx. This is 2 by pi square root. Now I need 2 with it. Alright, I need 2 with this one and 2 with this one. So it means I need to divide by 2, divide by 2. So this 1 over 2 times square root of 2 will become 1 over square root of 2. So this will become 1 over 2 square root of 2 pi 0 to infinity fs alpha, and 2 sine alpha cos beta is sine alpha plus beta and plus sine alpha minus beta, so it's x minus ct. Because in alpha and beta, alpha is common, so that's why I took alpha common, x minus ct, x plus ct dx. It's once again it's 1 over 2 pi 0 to infinity gs alpha over c alpha, and here 2 sine into sine becomes cosine minus cosine. All right, but cosine alpha minus beta comes first and cosine alpha beta comes afterward. So cosine alpha x minus ct first and minus cosine alpha x plus ct afterwards dx. So this is what I got. All right, call this equation star and we will simplify. This is very easy. This will become, because this is the Fourier inverse transform of fs, right? So this will become small f, but the variable will be x plus ct. So this is f of x plus ct and this is f of x minus ct. So this is the first one is very simple. It's just 1 over 2 times f of x plus ct, f of x minus ct. But this term has to be manipulated a little bit. All right. So let's see. Since gu is 2 by pi 0 to infinity gs alpha sine alpha x dx, right? I'm writing u, so I can write du. Let's say du. All right. Now if I integrate from x minus ct to x plus ct, this gu with respect to u, what you will be getting is 2 pi 0 to infinity gs alpha. This will remain there. Integration of x minus ct and x plus ct goes to just sine alpha u du, right? Because this integration is on u, right? So this is the only u factor inside, so I got it over there. Now what you got is 2 by pi 0 to infinity gs alpha. What is the integration of sine? It is cosine alpha u negative divided by alpha from x minus ct to x plus ct. d alpha is already there. d alpha, because I'm done with this integration, so d alpha is left. Now 2 by pi 0 to infinity, this is gs alpha over alpha, and inside is, because of this minus sign, I can take x minus cosine alpha, x minus ct first, and minus cosine alpha, x plus ct, and d alpha. Now you see this is the same, this is d alpha because we took the Fourier. We took the Fourier inverse transform, this is alpha, d alpha. So this is d alpha, d alpha. In inverse transform we take integration with respect to alpha. So in star this whole thing becomes this d alpha. Alright. So therefore star becomes uxt is equal to 1 over 2 f of x plus ct plus f of x minus ct. I just explained it before. And the last term, in last term I have c as well. This is 1 over 2 pi and this is square root of 2 pi. It means I will get 1 over 2 c outside. Alright. So I'll get 1 over 2 c outside, and I can write x minus ct, x plus ct, g u du. Alright. So this is the compact form of the solution, and it looks better, of course, than this one. Right? So of course, because these are known things, this thing is Fourier transform, Fourier inverse transform of f alpha. This is the Fourier inverse transform of f alpha with x replaced by x plus ct and x replaced by x minus ct. So that's why I'm getting in both form, I am getting my f back, but not at x, but x plus ct and x minus ct. And then I proved that the second expression, this expression can be written in this form. Alright, so I got this as a solution. Alright, so this is the solution of our wave equation in a semi-infinite string with the same, where one end is fixed. Alright, second end you have no displacement, so u goes to 0 as x goes to infinity, and partial u by partial x also goes to 0, and initial conditions are fx and gx. So see the contribution of fx and gx is coming in here. So if gx is 0, the second terms drop out, and you will get only traveling wave solution, which is fx plus ct plus fx minus ct. So the next topic is solution of Laplace equation. We will follow the same steps of Fourier transform technique to solve another well-known classical PDE, which is Laplace's equation. So let's start the solution of the Laplace equation. Solve the following boundary value problem in the half plane y greater than 0. In the half plane y greater than 0 described by partial to u by partial x square plus partial to u by partial y square is equal to 0. It's a two-dimensional heat equation, steady state heat equation, you can say that. Alright. Subject to the boundary condition, because it's a semi half plane, so y is greater than 0. So at y is equal to 0, we have a condition that at y is equal to 0, your ux is f of x. And of course, there is no other boundary. So what we can say that u is bounded as y goes to infinity, and also u and partial ux both vanish as x goes to plus minus infinity. Alright, so the solution of this equation is given by uxy is equal to y by pi minus infinity to infinity f of xi minus x square plus y square dxi. This solution is a well-known Poisson integral formula, and it is valid for y positive and when fx is bounded and piecewise continuous for all x. So let's see how we got this integral. By using Fourier transform, we will arrive at this integration. Let's see how we get this. So our equation is Laplace equation, right? Uxx plus uyy is equal to 0, and x goes from minus infinity to infinity, y positive, right? The condition is given that at y is equal to 0, we have f of x, where x is from minus infinity. So what is happening is, you have this is x, this is y. So you are considering heat equation in in half plane, right? So here, in here, you are considering your Laplace equation here. All right, y positive, right? So at y is equal to 0, this is your boundary. So this is y is equal to 0. So your u is f of x. At boundary, your function, your u is given. But what is happening as x goes to minus infinity and what is happening as x goes to plus infinity? We say that u and partial u by partial x go to 0 as x goes to plus minus infinity. Or you can say that as absolute value of x goes to infinity. Now, what is happening as y goes to infinity? So u is bounded. This is a second boundary condition, that u is bounded when y becomes very, very large. So it means these are the conditions needed for Fourier transform. It means we will be taking the Fourier transform with respect to x, that x will go to alpha and y be treated as the second variable, which is time in our wave equation. All right, so let's take the Laplace transform of equation 1. So take Fourier transform of 1. You will get Fourier transform of uxx plus Fourier transform of uyy is equal to 0. Fourier transform of uxx is minus iota alpha square Fourier transform of u, but this will become d2 by dy square, because y is treated as t, because y does not fulfill these conditions. All right, y does not fulfill these conditions as y goes to infinity. So this will be Fourier transform of u alpha is equal to 0. So what I got is, let's call this as capital U alpha t, right? Capital U alpha t. So we have d2 u by dy square plus minus alpha square u is equal to 0. All right. Again, this is a second order ODE, right? This is a second order ODE. So again, by considering the auxiliary equation, I can write m square is equal to plus alpha square. So m is equal to plus minus alpha. This implies that u alpha t is nothing but a u alpha y. So a alpha e to the alpha y plus b alpha e to the minus alpha y. Since u alpha y, since u x y is bounded as y goes to infinity, since u x y is bounded as y goes to infinity, its transform should be bounded as well. Alpha y is also bounded as y goes to infinity. All right, so this implies that your a of alpha should be 0 when alpha is positive. See, if alpha is positive, y goes to infinity, e to the power alpha y goes to infinity. So this will not be bounded. This will become unbounded as y goes to infinity. So we have to force this coefficient to become 0, so that this terms drop out and you get just b alpha e to the minus alpha y. Now if y goes to infinity, e to the minus alpha y will become 0. All right, and if alpha is negative, then this term will go to infinity as y goes to infinity. Then b alpha should be 0, and b alpha should be 0 when alpha is less than 0. All right, so this implies that your u alpha y should be equal to some constant times e to the minus alpha y. Let's call it e to the absolute value of alpha y, because in both the cases I'm getting either a constant time e to the alpha y or a constant time e to the minus alpha y, depending on alpha positive or negative. Means this implies that u will become b times e to the minus alpha y. So when alpha is positive, you are getting minus alpha y, and when alpha is negative, you are getting a e to the plus alpha y. Now you see, if alpha is positive here, you will get e to the minus alpha y, and when alpha is negative, you will get minus minus plus alpha y. So in both cases you can write e to the absolute value of alpha y. Now you don't have to say that alpha is positive or negative. It will automatically make it bounded as y goes to infinity. Now your boundary condition, one boundary condition was given to you, that ux0 is equal to f of x. Right? This was the first boundary condition. Now ux0 is equal to f of x implies that if I take the Fourier transform, this will become u alpha 0 is equal to f alpha. Right? So if I use this thing, this means that the constant which is being multiplied will give you f alpha. Because if y0 equal to 0, e to the power 0 becomes 1. So u alpha 0 is just a constant, and that constant has to be equal to f alpha. Alright? So this implies that u alpha y is equal to f alpha e to the minus alpha y. This is what you got. Now you don't have to restrict alpha to be positive or negative. It is valid for both alphas. Now what is f alpha? F alpha is 1 over square root of 2 pi minus infinity to infinity, inverse transform of small fx, right? Dx, alright? Dx, d alpha. Inverse transform uses d alpha. We are not taking the inverse transform, we are just replacing this by its formula. This is the Fourier transform of fx. So fx e to the iota alpha x and dx. This will be your transform. So because this is a function of y, I brought this inside the integral. Doesn't matter because the integral is with respect to x. Now take the inverse transform. Take the inverse Fourier transform, our uxt back. Uxt is equal to 1 over square root of 2 pi, and there will be one more 1 over square root of 2 pi because of the Fourier inverse transform. You will get minus infinity to infinity of inverse Fourier transform e to the iota alpha x, right, of this whole thing, minus infinity to infinity, fx e to the minus alpha y e to the iota alpha x dx, and times e to the minus iota alpha x d alpha. This is what you will get. Alright? So this will become 1 over 2 pi. Here you see this is a dummy variable x, and then one more x comes out. So this is not dummy, this will remain there. So there is a confusion in a dummy variable and which is not dummy, and both are x. So the dummy variable can be replaced by some other variable. Let's call it xi. Let's call it xi, and now there is no problem. Now x and xi are different here. Alright, so what you can write is minus infinity to infinity, minus infinity to infinity, fxi dxi, which is not in this integration. Let's say fxi dxi can be brought out because with this integration, I can keep this with this integration, fxi dxi, and then you have minus infinity to infinity all the other things, which are x e to the power, you have xi, iota xi and iota x. So if you take iota xi as common, it will become xi plus x. So you got alpha iota xi minus x and minus alpha y d alpha. The terms which contain alpha I kept with this integration, and the terms without alpha I kept with dxi integration. Alright? So far you have this thing. So let's simplify this. Let's simplify this one, what you get. Let's simplify this. Call it star, and I will simplify this exponential term. Now consider this one only, minus infinity to infinity e to the power alpha iota xi minus x and minus alpha y d alpha. Let's consider this one, and then we will replace the simplified value of this integration in our star, in our solution. Because alpha takes different values in positive and negative, so we can split our integration from minus infinity to 0. So this will become from minus infinity to 0, this will be minus alpha. So I will get iota xi minus x plus alpha y, because alpha is negative alpha, so this will become plus alpha d alpha. And from 0 to infinity, this is plus alpha, so I'll get alpha common, iota xi minus x minus y d alpha. Alright, so now if we integrate, it's e to the alpha iota xi minus x plus, sorry, there is no alpha because I took this as common, so y divided by iota xi minus x plus y from minus infinity to 0 plus e to the alpha iota xi minus x minus y divided by minus y from 0 to infinity. And now if you take alpha to be 0, e to the power 0 is 1 over y plus iota xi minus x, and at minus infinity, as what you can do is you can write this as take minus alpha as common, and you will get y minus iota xi minus x, and of course y minus iota xi minus x times negative sign. So when you put 0, you got this one. When you put minus infinity, e to the minus infinity will give you 0. So no contribution from there. Plus when you put infinity, e to the minus infinity will give you 0, and then minus 0 will give you minus 1 over y minus, you can put plus here, xi minus x. This is what you will get. Alright. Now if you sum them up, if you take the LCM, y plus and y minus, this iota will be cancelled. You will get 2y over y square minus iota square xi minus x square. So minus iota square is plus 1, so you got 2y over y square plus xi minus x square. This is what you got for minus infinity to infinity, e to the power alpha iota y minus x and minus alpha y d alpha. So therefore star becomes, if you go back to star, this thing becomes this integral, right, dy over xi. So what you will get is, so therefore your uxt becomes 1 over 2 pi minus infinity to infinity 2y f xi over y square plus xi minus x square d xi. So you can, 2y is common here, so 2 and 2 are cancelled. You can write y by pi minus infinity to infinity f xi divided by y square plus xi minus x square d xi. So this is what you will get as your solution, uxy. So when you integrate this thing with respect to xi, of course this will be a function of x and y. Alright, so this is your solution, which is called the Poisson integral, which I wrote in the beginning, that our given problem should have the solution of this form, and we were able to prove it now. Alright, so that's it for the Laplace equation. So we solve this boundary value problem in the half plane y greater than 0, described by this Laplace equation subject to this boundary condition, and we imposed other conditions as x and y goes to infinity, and the solution is of this form, and we were able to prove exactly this form of the equation. Let's see another Laplace's equation. Solve the following Newman problem described by the same equation in the half plane, but the condition is replaced by uy x0 is equal to f of x. In previous example, it was ux0 is equal to f of x, Dirichlet problem. In the Newman problem, you replace the condition with the derivative. Now ux0 is not f of x, rather uy of x0 is equal to f of x. That is the derivative of u with respect to y is given at y is equal to 0, which is the only boundary. All other three boundaries are at infinity. So we only impose the boundedness condition, and that the u and partial u by partial x both vanish as x goes to plus minus infinity. So here you can define, because uy is given at y is equal to 0. So this is one way of solving it. You can use the Fourier transform directly and solve very similar to what we did in the previous example. All right, but there is one more way of solving this Newman problem, that you replace your uy xy by phi xy. Let's call uy xy is phi xy. Then the given partial differential equation will become phi xx plus phi yy is equal to partial by partial y of uxx plus uyy is equal to 0, and phi of x0 is equal to f of x. Because this will become phi, uy is phi, x0 is equal to f of x. This will become phi x plus phi yy will be equal to partial by partial y of phi uxx plus uyy. From your equation, what is phi xx? It is uyxx. And what is phi yy? It is uy of yy. So this is the partial derivative with respect to y of uxx plus uyy is equal to 0. So from here, what we have done is we have converted our equation. We have converted our equation with a Newman condition to the same equation in phi with the Dirichlet condition. We have converted this problem to this problem which we just solved. This problem in phi xx plus phi yy equal to 0, phi x0 is equal to f of x is exactly this. By using this function, by defining this function, I have replaced my equation to the Dirichlet problem, and we know the solution of the Dirichlet problem is this. We just found out that. But this will not be a solution of u, this will be a solution for phi xy. So our phi xy is this, but phi xy is partial u by partial y. Now I can integrate this with respect to y to get my u. So u is integration of partial u by partial y. So if you integrate this thing with respect to y, you can get this one very clearly. What is the integration of this thing? Because this is the integral with respect to y, so I can bring it inside y f of xi divided by this whole thing, and then integral of this y over xi minus x square plus y square is nothing but log of this denominator. What is the derivative of this whole thing? Is 2y dy. So if I use 1 over 2 outside, this is the log of the denominator. So I got the answer of the Newman problem as 1 over 2 pi minus infinity to infinity f xi log of x minus xi square plus y square dxi. All right. So instead of using Fourier transform on this equation, we used our previous knowledge of Dirichlet problem to get the solution of this Newman problem. But if only the Newman problem is given to you, and the question is solved with the help of Fourier transformation, then you have to take the Fourier transform and solve this whole thing to get the final answer as this. Here we used it just because we just solved the Dirichlet problem before, where ux0 was f of x, and we had the solution for that problem. So we converted our new problem to the old one and used the solution of the old problem to get the new solution. So if you are doing the both problems simultaneously, then we can use one solution of the first to solve the other one. But if only one question is being asked, you have to prove everything. All right? So one more example here, solution of the Laplace equation. Using the method of Fourier transform, solve the following potential problem in the semi-infinite strip described by partial to u by partial x square plus partial to u by partial y square is equal to 0. X goes from 0 to infinity and y goes from 0 to a. Subject to the boundary conditions, ux0 equal to f of x. And now because we have three boundaries, x equal to 0 is one boundary and y is equal to 0 and y is equal to a is another boundary. This is an infinite strip because we contained y between 0 and a. It's an infinite semi-infinite strip from 0 to infinity, but y is confined between 0 and a. So it's a strip, all right, not a half plane. So here we have a three boundary condition. For the fourth boundary, we say that u and its derivative should go to 0 as x goes to infinity. So by taking Fourier transformation, again, it's very easy. This will be converted to iota alpha square u, and this will be d2u by dy square is equal to 0. Again, your solution will be in cosine and sine form. All right. By using these 0 conditions, you can easily obtain, because these are the conditions on y. Y is equal to a and y is equal to 0. Right? Y is equal to 0 is f of x and y is equal to a is 0. U at 0 is also 0. So if you use these boundary conditions, you can simplify your answer. All right. So following the same steps, you can easily find the solution of this Laplace equation. So I'm leaving this example for you as a little exercise of Laplace Fourier transform method. If you do it right now, just after watching this lecture, if you start doing it, then you will be able to solve it completely, and that will reinforce the ideas which we learned today. All right, and it will be very, very beneficial. If you leave it for tomorrow or some other time, a lot of things will be skipped out of your mind. All right, and it will become difficult to solve it. So do it right now, just after watching this lecture, or today, whenever you get the time, but as soon as possible. And if you are able to solve it, it means you got the idea of Fourier transform technique to solve partial differential equation. I write you the final answer so that you can compare your solution with my answer. So another example of Laplace transform, you had u x plus u y is equal to 0. X goes from 0 to infinity, but y is between 0 and a. All right. So boundary conditions are u at x0. U at x0 is equal to f of x. This is for y is equal to 0. Condition on y is equal to 0. X goes from 0 to infinity. And u at xa, the other boundary of y. This is 0, homogeneous condition. Again, x goes from 0 to infinity. And the third boundary is when x is equal to 0. This is also homogeneous, and it is for y 0 to a. All right. So u and partial u by partial x go to 0 as x go to plus minus infinity. So these are the conditions. So your problem is in this infinite plane. Your problem is this. X goes from 0 to infinity. So this is your one boundary. All right, this is your one boundary. X is equal to 0. And the second is y is equal to 0 and y is equal to a. This is y is equal to 0 and this is y is equal to a. So this is your problem is given in this strip, this infinite strip. It's going on till infinity. All right. So you have three known boundaries. So your u, when y is equal to 0, u is f of x. When y is equal to 0, when y is a, u is 0. All right. And when x is 0, your u is also 0 on the left side as well. So this is your problem. All right. So you have to take the Fourier transform with respect to x again. All right. Not y, because boundary of y's are fixed. Whatever has these properties, you should take the Fourier transform with respect to that variable. If you take the Fourier transform with respect to y, you will be in trouble because y does not satisfy these conditions. All right, only x satisfies this. So answer should be in integral form uxt So your answer should have this integral form uxt is equal to 2 by pi 0 to infinity f of xi 0 to infinity sine hyperbolic a minus y over sine a alpha alpha sine a xi sine alpha x d alpha dxi. So if you arrive at this solution, this is enough, because after that it will become very tedious. Means you may be able to further simplify it, but it will be very tedious work. So even if you arrive at this, it will be okay. All right. So why we are getting sine hyperbolic? Because the roots of your auxiliary equation were real and distinct. So in real and distinct, you can either write e to the power alpha x alpha y e to the power minus alpha y, or you can write cosine hyperbolic alpha y plus sine hyperbolic alpha y. So if you use that expression for your initial solution, you will arrive at this sine hyperbolic alpha minus y. All right. So try using that one, and you will arrive at this solution. All right. So with that, let's review what we have studied today. We solved wave equation using separation. So let's review what we studied today. We solved wave equation in half plane with the help of Fourier transformation, and then we went on to solve the Laplace equation with the help of Fourier transformation in half plane as well as in a half infinite strip as well. All right, so I left that for you guys and I wrote the answer. I hope you will be able to do that. Thank you very much for being with me throughout this lecture. I will see you in the next lecture. Till then, Allah Hafiz and Assalamu Alaikum.